In the end state, really what you can think about is a low-cost energy provider. So we provide power, cooling, and connectivity, and then anybody can do whatever they want with that.
So ultimately, if data centers in space become widespread, what impact does that have for the future of commercial space? This is the key question I asked Philip, the CEO of Starcloud. Philip proposes a radical idea: move all computing data centers from Earth to space. Why do this? Well, in one word, energy costs. The biggest customers of data centers on Earth are companies like OpenAI. Training a model like GPT-4 could consume as much electricity as is required to power a small town. The energy needs are growing quickly, and this results in high costs. Let's jump into why Starcloud wants to build data centers in space.
There's a few, but the two big ones are, number one, we get almost unlimited, very low-cost energy. And number two is we can scale them almost indefinitely. And so the other two are, the other sort of kind of advantages are we can passively cool them using sort of infrared radiation out into deep space, although that's kind of annoying because there's a vacuum and whatever. And also, once we're expecting to have much better connectivity than terrestrial data centers because we'll plug directly into one of the mega constellations. But the main biggest reason is energy cost. Energy costs will be much lower in space. Like the biggest constraint of building new data centers now is power.
What makes training large language models so power hungry today?
What makes an individual data center so power hungry is that the whole data center needs to be located in the same place and internally networked. So you can't run these distributed clusters, or there's work towards this, but at the moment you can't really run distributed clusters. You have to put 100,000 GPUs in the same location and have them all internally networked with fiber. It doesn't really make sense to have, it's not possible to have two different data centers training the same model. And so that means you might need to have several hundred megawatts in one very constrained location. And that means like basically building a new energy project every time you build a new data center. And the lead times on energy projects can be decades, whereas in space, we don't have that constraint. We can launch these things and build almost arbitrarily large data centers.
In the data center model that's in space, that's described in, like, say, the renderings on your website, you have a stem, and then you have a leaf going into each of these stems. So in theory, can you reconfigure some of these stems to, say, manage this sort of networked load of 100,000 GPUs?
That's the purpose of that stem design, is that all of the GPUs are located physically quite close to each other so that your networking is as efficient as possible. But the problem with having all of that stuff packed together is you then need to push all of that energy away from this very hot central core. So it requires active liquid cooling and very large deployable radiators. That's the core of the technical challenge, actually, is building very large, low-cost, low-mass deployable radiators.
Who are the primary customers of data centers in space?
So it depends on what time frame you're looking. In the early days, so in the first few years at least, the primary customers are twofold. Number one, it's an edge compute workload for other space users, so particularly Earth observation constellations and government satellites. Second is terrestrial customers who care about data sovereignty, you might call it. So, for instance, crypto people are interested in running nodes in space because they want to make sure they have redundancy. So these are the two main use cases.
In your Y Combinator pitch, you outline that Starcloud is building essentially AWS for space. So tell me more about that analogy.
It's a bit like, so the problem that many Earth observation satellites and government satellites have right now is they collect a lot of data and then they have to wait for a ground station before being able to downlink all of that data. And they, depending on the satellite, but they can very often not offload all of the data they're collecting. And so if they can connect into us in space using an optical terminal, rather than having to wait and use a very slow RF link to connect to a ground station, then they can ship all of that raw imagery to us, let's say. We then run some inference workload on that, and we just send down the insight. So let's say, for example, you're monitoring wildfires in California. You might have hundreds of gigabytes of imagery, And what you really want from that imagery is like a 1 kilobyte file that says, yes, there's a fire in this location moving in this direction at this speed. That is like a 1 kilobyte file versus 100 gigabytes of raw imagery to produce that. So we can produce that in space, and then we just downlink the insight rather than downlinking all of that data.
How does that compete with, say, the current Earth observation edge compute satellites that are out there? Is it 100x more powerful, 1000x more powerful, just because you have the power of, like, say, an NVIDIA GPU in there?
The demonstrator that we're launching in May, or was going to do, launch window opens in May, it'll probably be towards the end of summer, is about 100 times more powerful GPU compute than has ever been operated in space. So we're talking about data center grade terrestrial GPUs, essentially. And then the satellite, that one though is really a demonstrator, so that's designed, I mean, will be, it's to prove that our radiation shielding and thermal management techniques allow us to operate terrestrial GPUs in space. Then we'll be running a satellite that's about 100 times more powerful than that again in 2026, and that's the first commercial offering to customers. In terms of what people currently fly, lots of people say they're doing data centers in space, and what they mean is they're flying these like radiation hardened jets and chips and others, also from NVIDIA, but just not particularly performant. We're also flying with the jets and chip for the flight controls on our first satellite, but it's much less performant than the payload chips that we're flying.
So it's just a matter of like a customer saying, "Hey, we'll give you this chip, put it on your satellite, and fly it," and then the shielding is already designed.
AWS is not the best analogy, actually. A better analogy is somebody like CoreWeave, where we'll offer the compute time, and then we rent the compute time to somebody like AWS or Azure or whoever, and then they do whatever they want with it, and they run the architecture. Like they have their customers and whatever. We just provide them time on GPUs. So actually, in the end state, really what you can think about is a low-cost energy provider. So we provide power, cooling, and connectivity, and then anybody can do whatever they want with that.
What are the major milestones that you have planned, and how soon might we see, say, a fully operational data center in space?
I mean, it really depends what you mean by fully operational data center. We'll have very high performance edge compute capabilities in 2026. I think we'll have a 1 megawatt satellite before the end of 2030. And then I think we'll have a 40 megawatt satellite a couple of years after that. 40 megawatts is definitely a proper data center. Even 1 megawatt you could call a proper data center. But yeah, 100 kilowatts, maybe not. You wouldn't really call that a data center, maybe. But yeah, next year we'll have, we'll have the most powerful GPUs by 100x in space this year, and then next year we'll have 100 times more powerful than that again.
So Philip outlined his plan to put data centers in space. And building in space has its own advantages. Free and constant solar power from the sun, perfect cold sink for cooling the computers, and no regulatory constraints that are present on Earth. With these advantages, Philip explains how space-based data centers can achieve energy costs that are over 20 times cheaper than here on Earth.
It will be much cheaper. Our energy costs, once the launch cost comes down, so I will have to caveat this with everybody and with all investors, this is contingent on the launch cost coming down significantly, at least maybe more. And with Starship, it's projected to come down by 100x. Once that happens, then our all-in energy costs, including the launch costs, will be around 0.2 cents per kilowatt hour versus the lowest I've ever heard with nuclear for a new project is about 5 cents per kilowatt hour. So it will be, much more economic to do lots of things in space.
How important is Starship's launch cost per kilogram important to the business model that Starcloud is targeting?
In the longer term, extremely important. In the early days, we're just launching on Falcon 9, so we're targeting much higher value workloads. And so, we won't, in order to be competitive with terrestrial data centers, it's extremely important. In order to provide a useful service and build a profitable business using edge compute and other things, not that important. But I would, the reason I'm excited about the business in general is that I think all data centers are moving to space, and that does require low cost launch.
How does a potential customer like OpenAI shape your roadmap and your technology development?
We would love to partner with somebody like OpenAI, and we will, as soon as we've done the first demonstration, we will fairly proactively try and engage with the hyperscalers. We're already speaking with Microsoft. We're just down the road in Redmond, and my co-founder Eddie was there 20 years. So we had their entire data center leadership team in a room for an hour and a half a few months ago. They're very interested. I don't think they shape the roadmap, because what we need to deliver is actually pretty simple, which is like, if we can provide energy costs for under 1 cent per kilowatt hour, energy, cooling, and connectivity, then there is a market for it. Um, as I say, ideally we operate like a core reef. So we tell somebody like OpenAI or AWS or Azure, we have a bunch of chips. You can rent them out for X dollars per hour, and they rent them out for X dollars per hour. I don't see them. I mean, the way that OpenAI maybe would impact that roadmap is if they say, we want to put our own chips on your satellite and have our own internal networking architecture. We would be very open to that too. I mean, we can just be considered like a utility provider. We can provide you power, cooling, and connectivity, and you can do whatever you want with the space. Dump whatever chips in there, whatever networking architecture you want. We'll handle the running in space bit, shielding, thermal management, everything else, and you just log in as if you're logging into any API.
So Philip has made his case for moving data centers to space. But these large structures are prone to damaging effects from cosmic radiation, heat generation, and space debris. Here's how Starcloud is planning to mitigate these challenges. How do you essentially ensure that you have these servers reliably running for 10 to 15 years, considering the harmful effects of ionizing radiation?
10 to 15 years is ambitious. I mean, in a terrestrial data center, something like an H100 is not expected to last more than 5 years. So yeah, I wouldn't say we need, like, maybe the backbone infrastructure, like the solar panels and radiators, can last a bit longer, but the actual chips themselves, that's why we have these detachable modules, we're expecting to last about 5 years. Radiation is definitely solvable. So for the first few satellites, we're flying in what's called VLEO, very low Earth orbit. So anything below 400 kilometers, which is about 100 times less radiation there than there is where Starlink satellites fly, for example. I mean, Starlink network has pretty sophisticated chips on there already, and they don't have like crazy amounts of shielding. If you think about, I think 4 months ago probably 8 or 9 months ago now, there was one of the largest solar storms in the last few decades, and there wasn't a single Starlink satellite that went out because of that. So yeah, it's pretty impressive. And so yeah, radiation, as the satellite gets larger, that's when we'll be flying in probably higher altitudes. But it's also when the radiation becomes less of a problem, because the shielding scales with the mass of the satellite, volume of the satellite, surface area, sorry, and the compute scales with the volume. And so the percentage total mass trends towards zero the larger the satellite gets. And so, when we want to fly in these higher altitudes, the shielding will be less lower percentage of the total mass. And the last thing is,
But as you fly to higher altitudes, though, the radiation turns from proton dominated to electron dominated, which is worse. Am I not wrong in saying that? Because electron dominated radiation can, say, bit flip in a irreversible way, let's say, which is especially
that's what I
important
was
for
about to
compute.
come to. Well, for GPUs, bit flips are much less important than for solid state memory, for example. And also power. The two things that are affected by radiation are SSDs, like solid state memories, and power. Running an either an inference or a training workload on a GPU is actually not particularly affected by radiation, because you don't really care about bit flips, because there's a lot of stochastic randomness built into these models anyway. So a bit flip on a running an inference workload actually is not going to materially change the outcome. Whereas it obviously does for solid state storage or others. I mean, for the storage, we just pack as much shielding as you can. If the cost of launch really comes down, putting a bunch of lead around your SSDs is not going to be the end of the world.
So going back to, say, the mechanical challenges of building such a large solar array, such a large structure in space, I should say, is it an approach where we deploy very large structures and prove them out in incremental approaches, or take Lumen 1, Lumen 2, Lumen 3, Lumen 4, where you prove out specific parts of the architecture and eventually get to the 5 gigawatt scale?
I'll just say we will not be building any modular or docking capability until we hit at least 40 megawatts, because you don't need it until you hit that much. And 40 megawatts is one full Starship payload. 40 megawatts is absolutely massive data center on its own. So yeah, by that time, then the first iteration of docking is going to be 2 of these 40 megawatt data centers that dock together. And then the second or third iteration will be 10 of these 40 megawatt modules that dock together, and then scaling up and up and up and up, basically. You can do that in a way where you don't need even a backbone infrastructure. Each module can have all of the things it needs to support itself individually, and can have the networking to 2 other containers, and then
like each module can have a solar array and can have a radiator to cool itself. How concerned are you about space debris that it could potentially create? And is the current, say, FAA or currently acceptable debris mitigation plan sufficient to mitigate any large debris from, say, a 5 gigawatt data center?
A 5 gigawatt data center is going to require some thought. It is a bit of a beast. It's a very important question, and it's a high priority for us that we are a responsible space user. So for the early days, we'll be flying in this very low altitude. So VLEO, for your listeners who might not know, is a sort of self-cleaning orbit. So it's anything in that orbit deorbits within a few months. So very unlikely we're going to hit anything while we're in VLEO. You really want to avoid the most congested part of space, which is where the LEO satellites are flying, so between about 400 to 800 kilometers. So we probably will not be flying at that altitude ever. And then you want to, you want to then start flying again, maybe around 1200 kilometers. That's also a fairly clean orbit as well, because it's not a very desirable orbit to fly in because of the radiation. So if we can solve the radiation problem, then it's unlikely we're going to hit something up there. In terms of like end of life and demisability, the satellite will need to be fully demisable. So our first satellite is fully demisable, as in when it will burn up on re-entry, basically, when it's at the end of life in the upper atmosphere. So nothing will hit the ground from that.
Do you think customers are actually concerned about where their data centers are located, or is it agnostic?
Really depends on the customer. I mean, there's certainly a subset of customers who would pay more to run it in space than terrestrially, and I've mentioned a few of them. In the end state, we aim to. It shouldn't matter to the customer where the data center is. So we'll be, obviously everything will be end-to-end encrypted, but not only that, it will be. They have this concept called confidential compute, where even the algorithms, like we might receive data and then process it and ship it on, but even the processing will be encrypted. So we won't even know ourselves what is being done to that data, but what's being shipped on. So our customers in the end should not know whether we're in space or on Earth. It should not be a relevant factor to them. It should just be price. Can we give you compute time for cheaper than anyone else? And if we can, then they'll use us.
What do you predict the breakdown will be in terms of whether they're government customers or commercial customers?
I mean, in the end state, almost all commercial, because almost all, if you just look at the breakdown of AWS and Azure, it's almost all commercial. Yeah. And they have some very high value government work customers as well. But in terms of total percent revenue, almost all of it's commercial.
Okay, the technical challenges are hard, but ultimately, if data centers in space are successful, what does that mean for the space economy? What does that mean for the economy here on Earth? For one, Offering computing resources at significantly lower costs will make training the next generation of AI models economically feasible. Let's jump into my chat with Philip to learn more.
Data centers in space is actually like in my opinion, it's like the last business ever. Maybe I'm drinking my own Kool-Aid too much. But like we're essentially on a path to building a Dyson sphere at some point, and or you might call it a Matryoshka brain, which is a Dyson sphere hooked up to as much compute as a star system will physically allow. Like if you consider what proportion of the economy in 1,000 years' time will be data centers in space, it'll probably be 99% of the economy. So I mean, that's, in my opinion, is where we're heading. If you mean like in the short term, like in the 50-year time frame, like data centers in space will mean that we'll develop a lot of very useful technology in general. So one of the key pieces of technology we're building is a large, low-cost, low-mass deployable radiator. That is useful for almost all aspects of space. For example, if you're going to do asteroid mining, you're going to need to do refining in space. That will require dissipating heat in a vacuum. To dissipate heat in a vacuum, you're going to need a very large, low-cost, low-mass deployable radiator. If you want to build space hotels, that is probably going to have a concentration of heat that you want to dissipate, like the ISS does. If you want to build manufacturing facilities in space, that will need to dissipate heat in a vacuum. So, like the technology we're building.
I know companies that are exactly doing every single thing that you just mentioned. Space stations, asteroid mining. I think we have 2 companies now that are doing asteroid mining. It's incredible what the technology defined, which is low cost deployable, large deployable space radiators.
There's like a world where we pivot and become a space radiator company, and we become extremely profitable just doing that.
I would like to close out with one of my favorite questions that I ask on the podcast. I ask almost every single guest this question, and that is of contrarian bets. So contrarian bet is one that defies conventional wisdom. An example is SpaceX betting on making reusable rockets, and the whole industry thought it was impossible, but here we are today. Besides building orbital data centers at Starcloud, what is your contrarian bet?
I was going to say, do you not think that 5 gigawatt, 4-kilometer data centers in space are contrarian?
It's contrarian enough for me, but I want to know more. What else do you think is contrarian?
Contrarian
that you see today?
And right, because contrarian on its own is easy.
Right. That is a successful contrarian bet. And I think I got this question from Mark Manson because of Subtle Art of Not Giving a Fuck. Because he talks about the importance of placing the right contrarian bet.
Yeah, Peter Thiel always says, what do you believe that nobody else believes? Or what do you think is correct that nobody else thinks is correct? Well, I can prove one because I posted on it yesterday, and I have empirical evidence that it's contrarian. The post I did on LinkedIn was, do you think that we have already passed the AI singularity, or the event horizon of the AI singularity? And 80% of people do not think we have, and I'm one of the 20% of people who do think we have.
I guess I did vote yes, and I saw 24%. I'm like, really? I thought we did.
Yeah.
That's a great answer. Well, Phil, this has been an awesome conversation. Thank you so much for coming on. It's been a long time in the making, so I really enjoyed talking with you. I wish you guys all the success, and I'm looking forward to Lumen 1 or Lumen 2. No, Lumen 1 launching in...
Lumen 1.
Lumen 1 launching in the...
We might still call it Lumen 1 just for fun. Even though it's Starcloud now.
Yeah, that's exciting. So thank you for being on. I appreciate it.
Thanks so much for having me.
If you stayed till the end, thank you. And make sure you tell me what you liked about this video in the comments. And tell me what we should dive into next. Make sure you hit subscribe on this video so you don't miss an episode. See you next time.